Greetings and welcome to the video for problem set number 2 of Chemistry 223, where we're going to look at chapter 13 and learn about equilibrium, which is kind of cool. This problem set, like the previous problem set, is something you should self-correct before you turn in. So here are some hints just to get you started. Once again, try to use the periodic table found at mhchem.org/pertab. I think that'll be a good one. You don't have to watch this video from start to end. You can kind of scrub around it, move around. You can make my speed faster so I sound like a chipmunk. Whatever you need to do, it's totally fine. But most importantly, make sure that you mark every problem on your problem set. So the problems you get right, put one of those self-correct symbols next to it so that I know that you know that it's right. And if you do miss a problem, it's totally fine. Just like cross your old answer out, put the actual answer in, make some notes, maybe how you do better next time, and that's perfect. If you turn in a problem set and everything has been self-corrected, full credit, even if you get all the questions wrong. On the other hand, you turn in a perfect problem set, but you don't self-correct, you will not get full credit. So it's kind of important. If you have questions on this material, you are absolutely welcome to reach out to me. I can help. You can also talk to the Avid LSC Center located above the library. Their website is mhcc.edu/avid. They have free chemistry tutoring for you as a Mount Hood Community College student, and I encourage you to check them out. Okay, so without further ado, let's get into this problem set. So this first question says, write the equilibrium constant expressions for these 4 different reactions, all right? And an equilibrium constant, K, it's always defined as products over reactants. Products over reactants can be moles per liter, which I'll use concentration a lot. They can also be sometimes the pressures if it's a gas. In an equilibrium expression, you never want to put solids or liquids. You only want to include the aqueous parts if it's a water-based system, or gases if it's a gas-based system. There are 2 types of answers on A that you could put down. The one on the left, it just says K. Technically, that's a K sub C. And a K sub C is a concentration or moles per liter based thing. So notice that ozone, O3, and oxygen, O2, are both gases. They could both be moles per liter, or they could both be pressures, but we'll assume they're moles per liter. So notice that products, O3 on top, and reactants, O2 on the bottom. There's a stoichiometry of 2 by the ozone, and you can see that it's squared. So the squared part comes from that 2. And the same thing for the oxygen. You've got a 3 right there on the stoichiometry, and there's a 3rd power right there. The one on the right is a K sub P. It's a pressure-based equilibrium constant. K sub P's use pressures in atmospheres to figure them out. So in this case, because these are gases, you could do Kc on the left or Kp. Either one is fine. If it's a Kp, it would be the pressure of ozone squared, because again, that stoichiometry pops in. And you divide it by the pressure of the oxygen to the 3rd power. And again, for this problem, either way is fine. The next one is similar. Again, products over reactants don't include solids and liquids. And notice how the iron is not part of this, and that's good. So you would have it as FeCO5 on the top and CO to the 5th power on the bottom. So again, the left is a K sub C and the right is a Kp. And you can have either one because these are gases. Gases can be moles per liter. They can also be, though, a solution or something, or they could be a pressure in atmospheres. The next one is similar, but notice that the whole reactant side is a solid. In this case, you would just divide by 1. All right, so if everything is a solid or liquid, then you just ignore it. So Kc would be the ammonia squared times CO2 times water, and you would just divide by 1. On the Kp version, it would be the pressure of NH3 squared times the pressure of CO2 times the pressure of water, and again, divide by 1, and either way is fine. But the last one you really kind of have to do is just K sub C. These are not gases now, these are solutions, and you have ions in the solution. So the only one you would be able to write here would be a K sub C. And again, the reactant is a solid, so there's nothing in the denominator. Silver plus squared times sulfate would be Kc, and you're good to go. The second question, the equilibrium constant K for this reaction is 3.9 times 10 to the minus 3 at 300 degrees Celsius. And we have this mixture here of these gases at the following concentrations. And it says there the NaCl, the NO, and the Cl2. And it says, is the reaction at equilibrium? And if not, which direction does the equilibrium need to shift in order, or the reaction need to shift in order to come to equilibrium? And I like to use the idea, this is like if you're baking a cake in the oven and you're not totally sure if the cake is ready or not. So what people will do is they'll put a little stick or something like that in there and stuff, and they'll try to see if it's ready, and if this stuff sticks to it, then you have to keep it cooking, blah, blah, blah. Well, chemists have an equivalent. We want to know if this reaction is done. Is it at equilibrium? And we have these values of NaCl, NO, and Cl2. So if there's a question, if the reaction is at equilibrium or not, i.e. does it need more time to cook in the oven, you can do what's called a Q, a reaction quotient calculation. And reaction quotients have the same exact kind of look as an equilibrium constant, but we're going to compare the Q to the known value of K, the 3.9 times 10 to the minus 3. So for this reaction, looking at the top there, where's the actual reaction, the Q will be the NO squared times the Cl2, products on the top, reactants on the bottom. And in the bottom, you would have the NoCl squared. And to figure out Q then, you would literally just use these different numbers. Because again, we're not sure if this reaction is done or not. So the NO is 2.5 times 10 to the minus 3 squared. Don't forget that because of the stoichiometry. We multiply it by the chlorine value. We divide it by the NoCl, which is also squared because of that thing. And the Q value comes out to be 5.0 times 10 to the minus 4. And you'll see that that number is quite a bit less than the K, 3.9 times 10 to the minus 3. So that means our reaction is not at equilibrium yet. We need to leave that cake in the oven. It's not quite ready to come out, all right? Now, to know which direction this reaction is going to shift, Q will eventually become K, all right? When everything's said and done, equilibrium constant K, that 3.9 times 10 to the minus 3 describes what it is. So if Q is going to be like K, it has to become a bigger number. Right now, it's a 10 to the minus 4, and it wants to be 10 to the minus 3. It needs to get bigger. The only way that a number like Q or K can be bigger is if you have more products and or less reactants. So if you need more products, less reactants, that means this reaction is going to shift to the product side, to the right, because it will get bigger that way as you have more products, less reactants. Your 10 to the minus 4 will go to 10 to the minus 3. You should be good to go. This is how chemists see if a reaction is done or not. Next question, we've got an equilibrium mixture of SO2, O2, and SO3 at 1000 Kelvin, and it has these gases at the following concentrations. And we want to calculate K sub C, and there's the reaction that's given. Okay, so first of all, notice that this is at equilibrium, and that's going to be important. So we know that our cake is done from the last problem, all right? We know that we're not thinking about if the reaction is at equilibrium. It is at equilibrium. So we can use these informations then to figure out what the K value is. And K, products over reactants, the SO3 squared goes on the top, SO2 squared on the bottom, O2 on the bottom. Put those numbers in from the previous problem. K comes out to be 279. So that's one way to calculate then an equilibrium constant. You have to make sure that you're at equilibrium, and that's important, but if you are, then you literally just plug those numbers in. You're good to go. Here's another kind of question. You place 3 moles of SO3 in an 8-liter flask at 1150 Kelvin, and at equilibrium, 0.58 moles of O2 have formed. All right, calculate K sub C for this reaction using the given SO2, SO3 is going to 2 SO2 plus O2. Okay, so now this is a different kind of problem because we've put so much of a reactant in of SO3, all right, and we want to figure out the value of K for this based on it. So if you look at that initial value, the 3 moles is initial, like how much we started with. And at equilibrium, 0.58 moles of O2 have been formed. So knowing all this, we can figure out what K is, and the best way to do this is to use an ice table. Now, ice tables and Ks almost always use moles per liter. Sometimes atmospheres, like we saw with Kp, but most of the time moles per liter. And before we go through the ice part, notice what we did here. 3 moles in 8 liters would be 0.375 moles per liter. And later on, we'll need that 0.58 number. 0.58 divided by this same volume comes out to be 0.073 moles per liter. So the SO3, the 0.375, is how much we started with, and at equilibrium, 0.073 moles per liter have been made. So, like I started to say earlier, an ice table here will be really handy. And in an ice table, you want to have initial amounts of the 3 things, the change of the 3 amounts, and the equilibrium values. And the 0.375 number, that's the initial amount of SO3 that was put in. Now, the problem didn't say anything about having any SO2 or O2 put in, so we're going to assume that those 2 numbers are 0. And then this number right here is going to be helpful to us when we figure out the equilibrium values. So let's look at this ice table. Initially, the first row right there, we started with 0.375 moles per liter, and we didn't have any SO2 or O2. But we know that at equilibrium, 0.073 moles per liter of O2 was formed. So notice how oxygen went from 0 to 0.073, so the change here means it increased by 0.073. Now, SO2 has a 2 in front of it. So SO2 is going to go up by twice the amount that O2 went up, or 2 times 0.073, and at equilibrium, 0.146 moles per liter. Now, you can't get something from nothing. So if O2 and SO2 were forming, the SO3 amount has to decrease. And because of the stoichiometry, that 2 SO3s right there, the SO3 will decrease as much as the SO2 increased. So if SO2 went up by 2 times 0.073, SO3 will go down by 2 times 0.073. So mathematically, 0.375 minus 2 times 0.073 is this 0.229 number. And that's the equilibrium value of SO3. That's the number we want to put in our K sub C. So now that we have the E part of the ice table, we got all the equilibrium parts, let's calculate what K is. It's going to be products over reactants. It's going to be the SO2 squared times the O2, the 0.073. We'll divide it by the SO3 quantity squared. K here, 0.073. So notice that, first of all these ice tables, almost always moles per liter. Don't use just moles. It'll be confusing to you, and it'll get really weird. We need to use the equilibrium values for K, all right, to figure out the K constant. And the stoichiometry of the reaction was really helpful in the change part right there. The reactant went down, the products went up, all right, we can figure that out from there. Pretty handy. Here's another kind of problem. Cyclohexane is a hydrocarbon, a compound with carbon and hydrogen, and it isomerizes, which means changes form, into methyl cyclopentane, which is very similar. And we find here that the equilibrium constant is 0.12 at 25 Celsius. So we initially or originally placed 0.045 moles in 2.8 liter flasks and stop right there. We're going to figure out molarity here in a little bit, moles over liter, and that's going to be the initial amount of cyclohexane. But anyway, continuing on, after we get through the initial cyclohexane, it wants to know the concentrations of cyclohexane and methyl cyclopentane once you get to equilibrium. Believe it or not, this is a pretty doable problem. We've got the equilibrium constant, 0.12. It equals products over reactants at equilibrium. We have the initial amount of cyclohexane, all right, but we don't have any of the methylcyclopentane to begin with. So we're going to use an ICE table to figure out what all these different parts are. So again, first part, moles per liter, 0.045 divided by 2.8 liters is the 0.016. That's the initial cyclohexane. And then, like before, let's set up the ICE table. ICE is going to have reactants and products. Cyclohexane is the only game in town, which means we only have cyclohexane to begin with. It's going to go down, and the methylcyclopentane, the other thing, is going to increase. So notice here what we're going to do. We're going to use X to represent the change of how much cyclohexane is decreasing and how much methylcyclopentane is increasing. And because we started with 0.016 moles per liter cyclohexane and we know it's going to go down at equilibrium, 0.016 minus X. And the other compound, the methylcyclopentane, at equilibrium is going to be just X. We can set this equal to the equilibrium constant, that 0.12 number, and that's what we see here on the right-hand side. 0.12 equals the methyl compound divided by cyclohexane, X divided by 0.016 minus X. This is one equation with one unknown. So to figure out what X is, we need to isolate the X. So first we would go 0.12 times 0.016. That's a number. And we'd also go 0.12 minus X. Now 0.12 times 0.016 is this number right here. And that minus 0.12x equals 1x, that guy right there. So if you add 0.12x to both sides, you get just the 0.0192 number on the left and 1.12x on the right. So divide both sides by 1.12 to get x by itself, and x comes out to be this number, 1.7 times 10 to the minus 3. That's the methylcyclopentane at equilibrium. And then the cyclohexane at equilibrium, 0.016 minus 1.7 times 10 to the minus 3, 0.014 moles per liter. So it's kind of cool how these kind of things can be done. In this reaction, we have a K sub P value, an equilibrium constant based on pressure. So notice that all the reactants and products are gases. That's good. And case P, 0.16 at 25 Celsius. Now, in this reaction, the enthalpy change is positive 16.3 kilojoules. Now, if you remember back from earlier chemistry classes, enthalpy change means endo or exothermic, and a positive number like that means that this is an endothermic reaction. And if you have an endothermic reaction, you should literally write in heat as a reactant because it's going to be helpful to us. So anyway, positive delta H means endothermic, and endothermic means heat is a reactant. You need that heat to make this happen. Exothermic, you'd have heat on the product side, and your delta H would be negative. But anyway, we can use this information to predict the effect on the following changes on the position of equilibrium. Basically, we want to know, are they going to shift to the product side, which means right? Are they going to shift to the reactant side, which is left, or will there be more change? And this is an example of Le Chatelier's principle. And Le Chatelier's principle is a powerful tool we'll use all the way through this course. And in Le Chatelier's principle, it helps you to predict how a reaction will shift when a stress is applied to it. And what it comes down to is that if you add something, Le Chatelier's principle says the reaction's going to shift to the opposite side. But if you remove something, the reaction's going to shift to the side you're removing from. So I'll show you an example of that. So the first one, we're adding bromine, all right? And bromine is a product. So by Le Chatelier's principle, when you add, the reaction shifts to the opposite side. Bromine here is a product, so that means this reaction is going to shift to the reactant side. We would say that this reaction will shift to the left. So again, we added bromine. Bromine is a product. It's going to shift to the opposite side, to the reactant side. That's why this is going to be a shift to the left. If you remove something, the reaction will shift to the side that you're removing. So we're removing here a reactant. NOBr is a reactant. We're removing NOBr. And by Le Chatelier's, if you remove something, the reaction is going to try and compensate and move to the side that you're removing. So it's also going to shift, in this case, to the left. You're taking away the NOBr. The reaction is going to try and fill it in and make more NOBr. So this reaction would shift to the left as well. Now, the next one, decreasing the temperature. Temperature is a question of heat, and if you're decreasing the temperature, you're making the reaction cold, and making something cold is like removing heat. So again, that's the punchline. Decreasing temperature, you're removing the heat, and if you remove something, the reaction's going to shift to the side of what you're removing. And as we talked about, endothermic means heat's a reactant. This is going to shift the reaction to the left. So if you have an endothermic reaction and you start making the temperature colder, putting in an ice bath or something, it's going to move to the reactant side, to the left. Now finally, this last one's kind of strange. We're going to increase the volume, all right? This only works with gases, by the way. But you can see in this reaction you have 2 moles of gaseous NOBr on the left, and on the right you've got 2 gaseous NOs and 1 gaseous Br2. So you have 3 moles of gas on the product side and 2 moles of gas on the reactant side. If you're going to increase the volume, you're going to make a lot more space for these molecules to move around. And roughly a mole of a gas is about 22.4 liters. This is nerdy stuff that only nerdy chemists know. But anyway, if you're making more volume, the reaction is going to actually shift to the side with more gas molecules. So because there are more gas molecules on the product side, this reaction is going to shift to the right. So this is a function only of gases. More volume, more moles of gas will go to that side. Less volume, of course, would go to the other one. Pressure is the opposite. If you increase the pressure, it'll go to the side with less molecules. It's kind of interesting. The last part of this question is what happens to this equilibrium if you add a catalyst? And the answer for if you add a catalyst is that it does absolutely nothing. It does not affect the equilibrium. Catalysts will make you get to equilibria a lot faster. There's always an initial time that it takes for the equilibrium to get set up. Catalysts will make that time a lot less, but it won't affect the equilibria. You won't have more product or more reactant, anything like that. So adding a catalyst does not affect the equilibrium. You can manipulate equilibrium constant numbers if you change the stoichiometry. So for this NO plus O2 making 2NO, we have a K value of 1.7 times 10 to the minus 3. The first question is, what happens if you basically multiply the whole reaction by 1/2? So you have half of an N2 and half of an O2 making just 1 NO. And there are reasons why this is good. So if you change the reaction by multiplying through by 1/2, you take that K and you raise it to the power of what you multiplied it. So in this case, we multiplied everything through by 1/2. We're going to take the old K and we're going to raise it to the 1/2 power. And that's the same thing, by the way, as taking the square root of. So if you want to figure out the new K, it would be the square root of 1.7 times 10 to the minus 3, or 1.7 10 to the minus 3 to the 1/2 power. The new K, 0.041. And it is so important that you and your colleagues are talking about the same reaction, same stoichiometry, because if you change those stoichiometries, your K values will actually change in the process as well. Now in the second one here, notice that this second reaction, it's the same as the given reaction, but we flipped reactants and products. So 2NO was a product, and now it's a reactant. And N2 and O2 were reactants, and now they're products. So we flipped the K. Products became reactants, reactants became products. And if you want to find the old K, you literally take the inverse of the old K. So you'd go 1 over K. That's what inverse means. 1 over 1.7 times 10 to the minus 3. This number comes out mathematically to be 590. So I put this up here because we're going to do some of these kind of manipulations. I also put it up here because it's really important. We're all talking about the same reaction in the same way, because the K can be quite different, as you can see, depending on how people talk about it. Ammonium iodide dissociates into ammonia and hydrogen gas if it's high enough and stuff, and it must be. It's placed in a gas, it's heated to 400 Celsius, and the total pressure of the flask is 705 millimeters of mercury. And it says, what's the value of K sub P when this is done? And again, K sub P is almost always done in atmospheres. So if you look at this reaction, the solid ammonium iodide breaking down to ammonia, NH3, and HI, those are gases, but the initial thing is a solid. So Kp is literally going to equal the pressure of ammonia times the pressure of HI. So if we could just find those pressures, we'd be good. And how we can do that is to use the total pressure right here. Now, the reactant was a solid, and it didn't have an appreciable pressure over it. And for every mole of NH4I that breaks down, you're going to have a mole of NH3 and a mole of HI. They'll be made in equal molar amounts or equal quantities. So what this also means then is half that 705 pressure, half that number, that's going to be the pressure of NH3, and half the 705 is going to be the pressure of HI. 1 mole of NH3 is made for every 1 mole of HI. That means that half the 705 pressure is NH3, and half the pressure of 705 is going to be the HI. Now we need to turn millimeters of mercury into atmospheres and then multiply them together. You can see here what I did in this example is I turned that first into atmospheres. So 705 divided by 760 is how you turn it into atmospheres. 0.928 atmospheres is the total pressure. And again, because half that pressure is ammonia and half that is iodide, you can take half that 0.928 or 0.464 atmospheres. That's the pressure of each gas. And then Kp is the pressure of ammonia times the pressure of HI, or 0.464 times 0.464, 0.215 is the pressure. So again, don't forget, stoichiometry, pretty important. Equal moles, so the pressures are equal. Half the total pressure would be gas A, half the other pressure would be gas B, etc. This problem is going to take a little bit, so we're going to break this down to a couple of slides. In this reaction, you're starting with acetic acid. And acetic acid is a real common weak acid. It's the active ingredient in vinegar. So next time you have vinegar on your salad or something, woohoo, acetic acid. But anyway, acetic acid is an interesting compound. It forms pretty strong hydrogen bonds. And when it does it, they talk a lot of times about a dimer of acetic acid, which is the part on the right. Now a dimer is like two individual pieces stuck together. So in this reaction, we have two of the monomers, the acetic acids by themselves, in equilibrium with the dimer, this piece on the right. And if you dig through all this stuff long, oh, here's the monomer dimer, by the way. Monomer is the regular acetic acid, and dimer is the product on the right-hand side. But anyway, the equilibrium constant, 3.2 times 10 to the fourth. That's a pretty big number. It's much larger than 1. This is a pretty product-favored reaction, which is kind of cool. So anyway, let's say that we have pure acetic acid, the monomer, at 5.4 times 10 to the minus 4 moles per liter. we can actually use this information to figure out the percentage of acetic acid converted to the dimer. And that's going to be a cool thing we'll see on the next slide. Now, the second part of this problem, which is a lot smaller than the first, it says, as the temperature increases, in which direction does the equilibrium shift? And it says, recall that hydrogen bond formation is an exothermic process. So remember, exothermic means that heat is a product. So later on, we'll write that in there again. Remember, exothermic means heat. But anyway, let's look at how you would solve this problem. There's the information, but a little smaller font. We're going to start this problem with an ice table. And again, ice tables, reactants, and products. Everything here is gaseous or aqueous, so everything goes in. Initially, 5.4 10 to the minus 4 moles per liter acetic acid, and none of the dimer. And by the way, I'll put a big D there to represent dimer. But dimer is going to go up by X. Equilibrium means you've got some of both, all right? So at equilibrium, you'll have just X. Now, acetic acid, the monomer, has a 2 in front of it. So for every X that the dimer makes, you'll have 2X of the monomer used up. So at equilibrium, 5.4 times 10 to the minus 4 minus 2X is how we describe this acetic acid monomer, and X is the dimer. And if you remember from before, the K value was given 3.2 times 10 to the 4th. So you can use the equilibrium, the E part of the ice table, set them equal to K. K is 3.2 times 10 to the 4th. Products X in the bottom, 5.4 times 10 to the minus 4 minus 2X squared. So remember that these numbers right here, you raise them to the powers. Now, the good news is that if you look at this equation, all right, you've got just X, one equation, one unknown. We can totally solve it, but it's going to take some math. Now, if you have a TA89 or an Inspire or one of these kind of things, and you have that beautiful solve function, you can literally place this in just like this and solve for X, and it'll give you the answer. But in my day, back when I took Chem 223 and I had to walk uphill both coming and going from school and things like that. Anyway, we didn't have the cool solve function. Can you tell I'm jealous? But anyway, we had to use a quadratic formula. So if you wish to do this, and I encourage you to if you're interested, you need to break apart the 5.4 10 to the minus 4 minus 2x squared. So you go minus 2x times minus 2x is 4x squared, and then you've got minus 2x times 5.4 10 to the minus 4 and 2 of those, and you got 5.4 10 to the minus 4 times itself. But on top of that, then you multiply it by 3.2 times 10 to the 4th. And you'll have a big messy stuff. All of that equals X. You need to subtract an X from both sides, and you end up with this thing right here. And this is the form of the quadratic formula. The number that goes in front of the X squared is A. The number that goes in front of X, which is minus 70, is the B. And this 9.3 10 to the minus 3, that's the C. Now, quadratic formula, negative b plus or minus square root b squared minus 4ac over 2a. And again, this is the a in front of the x squared, b in front of the x, and the number there is c. And you plug all of this in, and you get 3.2 10 to the minus 4 and 2.3 10 to the minus 4 is your answers. Quadratic formulas always give you two answers. Now, this is where in chemistry you have to think a little bit. Most of the time you get a positive and a negative number, and you ignore the negative number. All right, no negative masses in chemistry. However, both of these numbers are positive. So in order to figure out which one of these is the bad number, if you look back at the monomer, the 5.4 10 to the minus 4 minus 2x part, if you subtracted 2 times 3.2, that would be 6.4 times 10 to the minus 4. So 5.4 10 to the minus 4 minus 6.4 10 to the minus 4, that would give you a negative number. And chemists don't use negative mass. So this number number is one you just want to ignore here. It's not going to be helpful in our chemistry world, which is obsessed with positive values for mass. X for this problem is 2.3 times 10 to the minus 4. So knowing that, you can go back and figure out the actual equilibrium concentrations of the monomer, which is this thing right there, 5.4 10 to the minus 4 minus 2 times this. And again, you get a positive number here. If you would have used the 3.2 number instead of 2.3, you would have gotten something negative, and that's bad. And the dimer is just equal to 2.3 times 10 to the minus 4. And notice here how the dimer is a bigger 10 to the minus 4 number than the monomer, 10 to the minus 5, and that's good because K was larger than 1, so we should have more products relative to reactants. If you can get to these two numbers right here, I'm very, very pleased. If you want to see the percentage of acetic acid converted into the dimer, then what you want to do is you want to take the amount that was reacted that turned into the dimer, which is the 2 times 2.3 part, and just divide it by the initial acetic acid, 5.4 10 to the minus 4. And you can see that 84% was converted into the dimer. So that's pretty cool. And that makes sense again because K is pretty large. If you increase the temperature, and if this reaction, like we saw, is, whoops, wrote it on the wrong side there. If, I can erase it here. If this is an exothermic reaction, so heat is going to be a product, and if you increase the temperature, you're adding heat. And since heat in an exothermic process is a product, when you add, it shifts to the opposite side, and the opposite side here is going to be reactant side. It's going to shift to the left. So this is kind of similar to what we talked about earlier. This is just an exothermic reaction instead of an endothermic. This is a reaction where we're thinking about how oxygen can form ozone, all right? So oxygen going to ozone. And the standard free energy change for this reaction is a positive number, positive 163.2 kilojoules per mole. Now, a positive delta G, it means non-spontaneous, and keep that in the back of your mind. Let's calculate Kp at this temperature. And remember, Kp is a equilibrium constant based on the pressure of gases, usually in atmospheres. And we'll look at the signs of delta G and K and make sure that they kind of make sense with each other. This reaction is another alternative way that you can use a delta G. Delta G equals minus RT natural log of K. And it's a whole bunch of types of K. This is a K sub P. So this is one way that you can take a delta G and turn it into Kp. Now, there's one tricky thing about it. R is 8.3145 joules per mole Kelvin. And you can see that delta G, like delta H, is usually in kilojoules per mole. So somewhere along the line, you either have to turn the kilojoules into joules, or you need to turn the joules and R into kilojoules. And I did the latter here. I turned this into a kilojoules by multiplying by 10 to the minus third. You could have also multiplied by 1,000 the 163.2 number. But anyway, at the end of the day, you're going to have numbers, not one number equals another number times natural log of Kp, and we can use this to find K. So if you do this, natural log of K equals negative 65.87, and I recommend you try the math to make sure you're good to go. We need to get Kp by itself, and that's where the anti-natural log comes in. And on the calculator, that's usually the E sub x button. It's usually second function ln or something like that. But e to the natural log, they cancel each other out. So that's why we have just Kp here. And then on the other side, you can go e to the power of negative 65.87. And again, this is where your calculator can help you. 2.48 times 10 to the minus 29. you can use these numbers and their magnitudes and see if they make sense. So up here at the top, we had a positive delta G. And remember, that's non-spontaneous, so that means you'll have a lot more reactant around than you'll have product. Now, K values that are less than 1 also mean reactant favored. So notice how a positive delta G and a K less than 1 correlate, and that's a cool way to check yourself. If our delta G would have been a negative number, the final K would have been a number larger than 1, product favored. So it's a nice way to check yourself on these problems if you get stuck. Okay, so that's it for problem set number 2. I sure appreciate you being here. If you have questions on the material, I encourage you to check out both the study and concept guides. They are located both online and in your companion. There's also the online-only chapter guides, which might have some information. There's also an important handout, Types of Equilibrium Constants, that will help us not only in this problem set, but in future problem sets. So keep that in the back of your mind. Again, I do appreciate you being here and spending your time with me. I hope this has been helpful. Good luck with your studying and have a wonderful day.